Hello everyone. In this video we are going to talk about one of the most common, useful and important topics in linear algebra, eigenvalues and eigenvectors. So the word eigen is a German word, means characteristic. So these are characteristic values and vectors of a matrix. How do we calculate them, and what's the meaning of this calculation formula? So if I have matrix A, then the eigenvalue of matrix shown by lambda and the eigenvector shown by vector v, the relation between A, V, and lambda is what you can see here. That if I multiply matrix A by vector V, it is going to be the same as what? Multiplying a scalar lambda by vector V. Okay, so this is how we define and calculate eigenvalues and eigenvectors. But first of all, what's the meaning of this? A times V equal lambda times V. Lambda times V is quite clear, right? We know when we multiply a scalar by a vector, what we are doing is to resize the vector, correct? Like if this number is 2, we make vector V 2 times bigger, but we do not change the line of action or the direction of V, correct? It's going to be on the same line of action, same direction, just 2 times bigger, or if lambda is, let's say, less than 1, going to shrink in size. If it's negative, it's going to reverse the direction as well, okay? But the line of action is not going to change whatsoever lambda is. But what is it that you're doing when you multiply a matrix by a vector? Well, in general, I can easily show you right now that when you multiply a matrix by a vector, the result, that is going to be another vector, it is going to be compared to V, it is going to be resized in general. So multiplying a matrix by a vector does change the size of V in general, and it also does change the direction of the vector. Now here it says, I'm interested in what? Those vectors such that when I multiply A by them, all I am doing is to resize them and not reorient them. Okay, if there are such vectors that when I multiply A by them, I'm only resizing them, those vectors are going to be called eigenvectors. And the scaling factor lambda is going to be called eigenvalue. Okay. Now, as I said, when you multiply A by V, there are two things happening. Let's take a look. So let's say here I go with something very simple. Let's say V in general is like, for example, 1 and 2, right? And matrix A is something like 3, 1, 4, and 2. So when I say A times V, let's see what happens. So when I multiply that by this, I get a 3 and a 2, that's going to be 5. Then I get a 4 and a 4, I get 8. Now, if you look at the slope of this guy is 2 over 1. The slope of this guy is 8 over 5. So although this is close to 2 over 1, but not exactly equal. So definitely, if this is V, if I can draw on the two-dimensional plane, if this is my vector V, 1 and 2, like this, then A times V is going to be 8 over 5, which is 1.6. So in 1 unit of x, it moves only 1.6 units of y. So this is A times V. Okay, so first of all, definitely the direction is that, but also the magnitude. So the magnitude of A times V is not going to be exactly this magnitude. It's actually larger. If you look at the magnitudes here, that's way bigger than these two. So that's the direction of AV, but not the entire vector AV. If you really want the entire vector AV, what you need is, that's only the line of action, okay? So it is going to be on this line, but how big? Well, if you look at size of V is going to be square root of 1 squared plus 2 squared, so it's square root 5 units. But if you look at the magnitude of AV, it is going to be the square root of 5 squared plus 8 squared. So that's 64 and 25, correct? That's 89. So that is the square root of 89. And that is 9.43. And for 5, it was 2.24. 224, 943. So you see, magnitude-wise, it is about 4 times or more than 4 times bigger. So A times V, it is going to be on this line, but 4 times bigger than V, so it's probably something like that. Okay, so multiplying a matrix by a vector will resize it and reorient it, correct? That's what it does. But now there are some vectors in general, maybe for this matrix, real numbers, because I'll show you later, the eigenvalues and eigenvectors are not necessarily real numbers. Sometimes they are complex numbers that basically if you multiply A by those, it only resizes them. So in MATLAB, I'll show you how we calculate eigenvalues and eigenvectors on the paper. But in MATLAB, you can use the command eig, correct? You can say V and D is equal to eig of, then you define your matrix, and here is 3142. So all we need is to type it in. And you clearly see that in this case, fortunately for us, the eigenvalues are real and eigenvectors are what? Real as well. And here, if I look, this is my first eigenvector, this element and this element. This is my first eigenvector. The corresponding scaling factor is 4.56. Why is that? Let me show you. So if I define my A to be the same matrix I had, it was 3 and 1, 4 and 2. And then I say V1 is equal to V of column 1. And V2 is V of column 2. Okay, so these are the two eigenvectors, right, that you can see. Then I say lambda 1 is D of 1 and 1, and lambda 2 is D of 2 and 2. Good. Now, let's see if that's the case or not. So if I multiply A by V1, this is the result. And then if I say lambda 1 times V1, this is the result. You see, they're identical. So what did I do when I multiplied this matrix by this vector, which is 0.53 and 0.82? All I'm doing is resizing it, not reorienting it, resizing it by a factor of how much? Lambda 1, which is 4.56. So here I wrote a code to help you visualize this. So here I have a V1 vector. I draw a line for it. I multiply A by it and show the result in a different color, and then do the same thing for V2, right? And if I do it, you can see the result here. The red one is V1 in thicker line. The blue one, which is 4.5 times bigger, is blue, AV1. V2 is what? The one in black, and AV2, which is in green, is like less than V2 in magnitude, and those scale factors are what? Lambda 1 and lambda 2, correct? Lambda 1 was 4.5, the one that got bigger, and lambda 2 for V2 that got smaller was 0.43. So you clearly see that the blue vector V1 got, the red vector V1 got larger, it got the blue one, and the black one, that is V2, got shorter, that's the green one. Okay, but if you see the direction of V1 and AV1 and then V2 and AV2 are the same, there is no change. But if I do any other vector, let's say here I just, for the sake of demonstration, I add another random vector for you here. So I generate a vector V3 and say this is equal to rand of 2 and 1. So these are two random numbers between 0 and 1, both in trees. And now here I do something like this, and here I use a different color, maybe yellow or maybe cyan, correct? And then I get AV3, and for that I use magenta color. Okay, so V3 and AV3 are going to be cyan and magenta, and I add a little bit of that as well here to clarify, right? So let's do it. So here we go. Now if you look clearly, the there's something wrong about the colors. V3, that's good. AV3 is good as well. Let's make sure. Red, blue, isn't everything good? Let's do it one more time. There we go. Here. So now if you see, the purple and the cyan are different orientations. And you might say, well, they are close. Yes, they are, but still they are not collinear. And if I change it one more time by running it again, so that my random vector is a different vector, now look again. Look at the V3 and what? AV3, you see? They are now quite different. If you want, we can run it one more time. Look, here, right? Let's do it again. Now here, this time they are very close. The thing is, when I do that, since rand command always generate positive numbers, so my vector V3 is always in the first quadrant. But if I do rand n, so now they can be negative as well. Now look, there we go. You see, now they are a little bit different. And now again, different, right? Now completely different. So the only two lines that will match this criteria, A times V equal lambda times V, are those two vectors V1 and V2. So we call them eigenvalues of A. We call lambdas eigenvectors of A, and lambdas eigenvalues of A. Good. So this is about the meaning and the use of them. Now, question number 2, how do you calculate them? How do we calculate them? So for calculation of them, we need to form what we call the characteristic polynomial, and then find through that eigenvalues and then plug them back into this equation and get eigenvectors. So how do we do that? Well, if A times V is equal to lambda times V, one of the things I can do, instead of lambda times V, I can write it as lambda times I times V. Okay? By the way, as you probably noticed, when I defined A was only a what? It was a square matrix. So this A has to be what? N by N. It cannot be a rectangular. And V is an N by 1. So this lambda is a 1 by 1. This I is an N by N similar to A. And this V is an N by 1. So when we define eigenvalues, it is only for a square matrix A. You might say, well, What about rectangular matrices, non-squares? Can we have such anything like that? Yes. And that's one of our future videos, okay? We call it the singular value. So we'll talk about that later. But right now, just keep in mind, we are only focused on square matrices. So you know I times v is the same as v. So I write it this way, and then I can bring this whole thing to the left side and factor out v. You will get a minus lambda I times v to be equal to vector 0. And this is a homogeneous set of equation. If I know my lambda and consider this a set of linear equation in terms of the components of v, right? This is a linear set of equations and is homogeneous, and we know a homogeneous set of equation only has any solution when what? When the determinant of this coefficient matrix is what? 0, correct? If you remember, please watch my video on solving set of linear equations. If you have a set of equations ax times b, if b is equal to 0, so the set of equations is homogeneous, the only time you can have solutions is when the determinant of this coefficient matrix is 0. How many solutions would that give you? Infinitely many. So what does it mean for v? Infinitely many? I'll show you. When we have infinitely many solutions for v, basically all it gives me is the direction of v, not exact single number for each one of the entries. Okay, so first condition is if I want to find any solution for eigenvector, the determinant of this guy, a minus lambda I, has to be equal to 0. And when we set that equal to 0, it gives us a polynomial. I'll show you. So when we say the determinant of this lambda I minus a is equal to 0, the result of that is going to be a polynomial. If this a is of order n by n, it gives you a polynomial pa of lambda, which is of form lambda to the n plus a1 lambda to the n minus 1 plus a2 times lambda to the n minus 2 plus all the way to an minus 1 lambda to the 1 and plus an equal to 0. Okay, so when you expand it, it gives you an nth order polynomial equal to 0, and the roots of this nth order polynomial are going to be what? N lambdas. So in general, your matrix A, which is n by n, is going to have what? N eigenvalues, and those are the roots of this polynomial, which we call what? The characteristic polynomial. Of A. Okay, so that's the first step, that's to find the lambdas. Once we find the lambdas, the next step is to find v's. But first, let's practice on something, okay? Let's get some lambdas and then we move on to v's. So let's say, for example, in this case, for this matrix, how do I find lambdas? I say the determinant of lambda times I of the same size as a 2 by 2, minus a is equal to what? Determinant of. If I form lambda I means it's going to be like lambda 0, 0, lambda, okay? That's what this guy would look like. And then subtract each element of a in it, so you will get lambda minus 3, negative 1, negative 4, and lambda minus 2. And the determinant of that is the product of the element on the diagonal minus the element on the anti-diagonal. This has to be equal to 0. So if I simplify, what do I get? The result of this is lambda squared minus 5 lambda plus 6. And then subtract a 4 from it, so you will get lambda squared minus 5 lambda and then plus 2 is equal to 0. And clearly you see that the roots are going to be lambda 1 and 2 to be equal to what? 5 plus and minus the square root of 25 minus 8 divided by 2. This is 17. So 5 plus and minus the square root 17, and a square root 17 is less than 5, so both numbers are going to be positive. And if we calculate them here, so 5 minus the square root of 17, the whole thing divided by 2, that's that 0.43 that we had, lambda 2, if you remember. And if I add them together and divide by 2, that is that lambda number 1 that I had. You see? So these are my lambda 1 and lambda 2, right? So one of them is going to be 4.56 up to 2 decimals, and the other one, it is going to be 0.43. Good? So these are my lambdas. Fine. Now that I got my lambdas, how do I get my v's? So now I go back to the original equation. The original equation of eigenvalues says what? Say A times V is equal to what? Lambda times V. Now, here, if I plug in lambda 1 in place of lambda, the result is going to be what? Right? Eigenvector 1. If I plug in lambda 2, it's going to give me eigenvector 2, or the eigenvector associated with lambda 2. So let's do that. And what I can do here is, again, I can bring the whole thing to the left side, multiply this v by I, and write it in the same way that we had before. So it was a minus lambda I, or lambda I minus a, it doesn't matter, right? So if you see here, correct, a times v equal lambda times v, or vice versa, there is no difference. So it's going to be a minus lambda I, or you see here I did the opposite of that, I did the negative of that. The determinant of lambda a minus I. That's the same thing. The result is the same, right? It doesn't matter whether you do lambda I minus a or negative lambda I plus a. The result is the same, because all it does multiplies this whole thing by a negative. And since the result is 0, it doesn't matter. So whichever one that you do, it's the same. So a minus lambda I times v1, this thing is equal to vector 0. Okay, let's plug in. So it is going to be a, which is 3, 1, 4, and 2, minus lambda 1, which is 4.56 on the diagonal, this is a minus lambda 1I times v1. Now this v1, I can call it v11 and v12, right? It's a 2 by 1 vector. It has two unknown components. Let's call them v11 and v12. This is equal to vector 0, which is also a 2 by 1, so it's equal to 0 and 0. And clearly here I have what? Two equations. If I expand it, the expansion is going to be what? This number is negative 1.56, and this number is negative 2.56, correct? So it is going to be negative 1.56 times v11 plus v12 equals 0. The other one is 4 times v11 minus 2 times 5, 6, v12 equals 0. Now, first of all, you might say, well, is the result going to be 0 and 0? No. The 0 and 0 is the trivial answer. The matter of fact is these two equations are the same equation. If you find the ratio of 1.56 over 1, that's the same ratio as 4 over 2.56. Okay, let's do that. 4 divided by 2.56, you see that's 1.56. So these two equations are the same equation, and they should be, because When we set the determinant of a minus lambda I to 0, it means my two equations are going to be only one of them independent, right? They are not going to be two linearly independent equations. Only one of them is really an independent equation. The other one will depend on it. So it only gives me one ratio between V1 and V2. Whichever one that I use, I can only use one of them because the second one is the same as first one. So if I use the top one, that gives me a ratio. It says, hey, V12 is equal to 1.56 times V11. That's all it gives me. Did it give me the answer for both of the V components? No, it only gave me a ratio. So what kind of vector is this vector? Well, it does not matter what number I choose for one of them. First of all, as I told you, there will be infinitely many answers. It's a homogeneous set of equations, what we have, and the homogeneous set of equation, this one here. This homogeneous set of equation, when the determinant of the coefficient matrix is 0, it's going to have infinitely many solutions, which clearly you can see here. I can choose any number for V11, it gives me any number for V12. So definitely I have infinitely many solutions, but among all of those solutions, there is one thing the same. That's the slope of the line. If you draw this in the V12, V11 plane, the slope of the line is 1.56. All that changing is the scale of that vector. And for eigenvectors, we do not care about their scale. All we care is the direction. So it doesn't matter what number you choose for one of them and get the other number. The direction of the resulting line is the same, and that's again all that matters. One of the things they typically do, they choose one of them to be a 1, and then they choose the other one. So one of the solutions might be 1 and 1.56. This is one way they can give you vector V1. Now you might say, well, in this case they didn't. If I look at V1, that's this guy. What did they do here? What they did is called normalization in this case. If I look at the magnitude of this vector, it is 1. So they made sure that the resulting vector V1 is a unit vector. This guy is not a unit vector. So what they do instead, they divide this vector by the magnitude of it, right? And that way they choose the final V1 vector. So instead they replace it with V1 over magnitude V1. This is what MATLAB does, and it gives you a unit vector, basically, a unit vector for V1. And if you do that, you should get what here you have, right? 0.54 and 84. The ratio between these two numbers is also 1.656. Okay, so this act here is called what? Normalization. They try to get you a unit vector for vector V1. Because if all that matters is direction, let's just stick to a unit vector. And it has other important properties, the fact that we go with unit vectors. I'll tell you later when we go back here and talk about the diagonalization and eigenvalue decomposition. I'll tell you why it is important to make them unit vectors, okay? But if you go back, that's what V1 is, right? So we got V1. Now we do a very similar approach for what? For V2. So again, we say A times V2 is equal to lambda 2 times V2. If I plug in lambda 2, the result should be V2. And that again means A minus lambda 2I V2 is equal to vector 0. And this time, the elements of A, they have to get a subtraction on the diagonal from lambda 2, which is 0.43. And instead of the whole vector V2, I show it with this component. I call it V21 and V22. this is equal to vector 0 and 0, again, it gives you two equations, but the two equations are going to be depending on each other. So this is going to be 2.57, and this is going to be 1.57. So it's going to be 2.57 V21 plus V22 equals 0, and then 4 times V21 plus 1.57 V22 equals 0. Again, the ratio between 4 and 1.57 is the same as 2.57 and 1. So both of them are going to give me only one equation. Again, if I use the top one, that means your V22 is going to be equal to negative 2.57 V21. Okay, and now again, what number do I choose? I have infinitely many solutions. It's up to you. You can choose, for example, a 1 here. If you choose a 1, that gives you a what? That gives you a vector like this, 1 and negative 2.57 for V2. And if you want, again, you can divide it by its magnitude and instead replace it by the magnitude, which is going to be vector V2 divided by magnitude of vector V2, which if you do should get you what MATLAB gave me. Correct? So here V2 was negative 36 and 93. And the ratio between these two is again negative 2.57. Okay, so this is how I have calculated my vectors V1 and V2, or their corresponding unit vectors, because that's, as I said, all matters is the direction of these. And I found the scaling factors. So this is how we calculate eigenvalues and eigenvectors. Now, before I get into the next topic, I need to talk about an important case, and that is when you have eigenvalues that are repeating. So if you have repeating eigenvalues, then there are two different scenarios that can happen. Either the eigenvectors for those repeating eigenvalues are going to be linearly independent, or they might be linearly dependent on each other. So you are going to lose basically n linearly independent eigenvectors. You might get like n-1, n-2, and so on. So let's look at a couple of examples. Case 1, let's say A is equal to 1, 0, 3, and 1, right? So if I set the determinant of A minus lambda I to be equal to 0, that means the determinant of 1 minus lambda, 0, 3, 1 minus lambda. You set that equal to 0, it means 1 minus lambda squared minus 3 times 0 equals 0. And so both of the solutions are going to be 1. Lambda 1 and 2, they are both equal to 1. There is only really one lambda. Repeating case. And the question is, okay, both of them are equal to 1. Now, how do you find the eigenvectors? Well, for eigenvectors, for both of them, since they are the same number, I have to use this relation that A minus lambda times I times the whole thing times V equal vector 0. So if I call it lambda 1 or call it lambda 2, in both cases, since the lambdas are the same, so it gives me a solution for V. So it doesn't matter really call it lambda 1 or lambda 2. So if I do that and plug in 1 here, right, then this coefficient matrix is going to be what? it is going to be, as you can see, 1 minus 1. That's a 0, a 0, a 3, and a 0. And then if you call this v vector to be two components, v1 and v2, the result of that is 0, 0. Then it gives you one conclusion, and the conclusion is what? The conclusion is the first row times this is going to be 0, so it's going to be 0 equals 0, which is obvious. The second one is going to be 3 times v1 is equal to 0. And that means v1, the first component, has to be 0. Well, what about v2? There is no constraint on v2. So v2 is going to be what? Arbitrary. So the form of your eigenvector v is going to be 0 and something, whatever. That something I can choose one time, let's say, to be 1, if I want to have the magnitude 1 for that eigenvector, and let's say another time I can choose it to be what? I can choose it to be -1, right? So both of these cases, they are unit vectors, they have magnitude 1, the first component in both of them 0, and you get 1 and -1. So these are the two eigenvectors, and if you run MATLAB, you're going to get the same result, right? So let me show you. So here is A matrix, and then I say V and D equals to the eigenvalue of A, right? And you see the eigenvalues are 1 and 1, and the eigenvectors, one of them is 0, 1, the other one is 0, -1. So exactly what I got. Right? Now, are these two linearly independent eigenvectors? No. If you see one of them is the same as the other, just multiplied by -1. And if I chose this to be any other number, 2, 5, doesn't matter. Remember, the second number is arbitrary. It doesn't matter. In all cases, these two are going to be depending on each other. One is going to be a scalar of the other one. So here you only have what? You only have one linearly independent eigenvector. You don't have two linearly independent eigenvector. If one of them is on some line, the other one is going to be on the same line. In this case, one of them is vertical up, one of them is vertical down. So it does not really gonna give you two separate directions. Now, not always we have the case that one of these eigenvectors is independent, the other one depends on it. There are some different scenarios, like what? Well, let's say here I change my A matrix to something a little bit different. Let's make it, for example, a 3 by 3 matrix this time, and say A is, for example, equal to. So here, let's say it is a matrix like this. And again, if I set the determinant of A minus lambda I equal to 0, you will get this matrix. And if you set the determinant of this equal to 0, you can use the Sarus's method, and it gives you a cubic polynomial, correct? So that's these two, that's 0, that's 0, this is 0, that's 0, and then you will get minus 4 minus lambda. Correct? This is equal to 0, and if you factor out, you'll get 4 minus lambda times 5 minus lambda squared minus 1, which is going to be lambda squared and minus 10 lambda, and then plus 24. Right? The result is 0, and so you will have some answers. So you know the root of this is 4. And here you have two numbers, the product of which is 24, the summation of which is -10. And so the numbers are -4 and -6. So it's lambda minus 4 times lambda minus 6. So lambda 2 is 4 and lambda 3 is 6. So as you can see here, I have two lambdas to be equal to 4 and one lambda to be equal to 6. Okay, and now the question is, for these two lambdas that are equal to 4, do I have two linearly independent eigenvectors or linearly dependent eigenvectors? So if I plug this 4 into here, right, which is a minus lambda I, this is going to be 0, you get the 1, you get the 1. So for lambda of 4, the format that you need is going to be 1, -1, 0, -1, 1, 0, 1/3, -1/3, and 0. This times vector v, which you can write it as v1, v2, and v3. This is going to be 0, 0, 0. And if you expand this, you'll get 3 equations, and if you look at all 3 of them, the result is the same. It's going to give you a ratio between V1 and V2. In all cases, the V3 is multiplied by a 0. And if you look at the ratio here between this one and this one, that's a -1, this is a -1, this is a -1. So all you will get out of all these 3 equations is only one equation, and then one equation is V1 equals V2, or V1 minus V2 equals 0. And what about V3? V3 is arbitrary. There is no constraint on it. So what kind of vector can I have? I can have one vector like, for example, what? 1 and 1. And maybe a 0, right? Because it's arbitrary. And I can have another vector where this can be, for example, 1, 1, and a 1. Correct? They are equal. This one is arbitrary. So these could be what? 2 of my eigenvectors. And now if you look at them, they are clearly what? Linearly independent from each other. Right, because this one has a component that is 0, this one does not, right? So this is like a kind of a vector on the xy plane. This is completely 3D. So now I have what? I have 2 linearly independent eigenvectors. For the repeating eigenvalues. So there are different scenarios that can happen, right? There are different scenarios that can happen, but the solution is just coming from the general relation that a minus lambda I times v equals 0. Okay? So hopefully I could clarify these 2 important topics, and I will continue in the next video by talking about eigendecomposition and properties of eigenvalues. Thank you.